Hello everyone, my name is Roberto Speranza and I am a Ph.D. student at Politecnico di Torino. My research focuses mainly on integrated harvesting and storage devices for a sustainable future. In my last post-day presentation, I presented the work that I did during my first year as a Ph.D. I fabricated some multi-purpose energy harvesting and storage devices that could power low-consuming IoT sensors in a rigid and flexible configuration. And I also collaborated in the fabrication of an integrated device able to reduce CO2 to high-value products, powering the reaction with solar energy. During my second year, I focused my attention on the optimization and advancement of the indoor powering systems. This is because I think that the energy demand of the ever-increasing IoT devices is an important problem to consider. Many of these IoT devices are low-consuming, distributed sensors that are usually employed in a high number and need to be powered locally without a connection to the grid. For this, batteries are a reliable option, but after their relatively short life cycle, they need to be substituted and recycled. That is why I think that an integrated device able to harvest energy from indoor light and directly store it can represent a viable and more sustainable alternative to batteries. So I am combining the high indoor efficiency of Dyson-style solar cells with the high power density and long cycle life of supercapacitor in an hybrid multifunctional device. During the work, I am following a strong application-oriented approach, selecting innovative materials and designs. Then, starting from these elements, I fabricate and characterize my devices and then, based on the results that I obtain, I optimize the prototypes following a closed feedback loop process. With this approach, first of all, I worked to improve the overall efficiency of my devices. Then, I also tried to improve some special features such as flexibility and scalability, and all of this trying also to consider the possibility of reducing the production costs of my devices. To improve the efficiency of the solar modules, working with Giulia Gianola, a master student in nanotechnology, we propose an innovative design that foresees a device with a shared bifacial and semi-transparent counter-electrode with two external semi-transparent photoanodes. This configuration allows to recover some of the incoming light that is not collected when a single photoanode is realized, allowing also a high level of bifaciality of the solar module. We observed a 20% increase in efficiency with respect to a reference module. Then, integrated this configuration with a supercapacitor, we also observed a 46% increase in the maximum overall photocharging efficiency. This is mainly due to the higher current generated by the solar module. Then, I also worked to find some solution to simplify and optimize the fabrication process of the solar modules. Here you can see a 5-cell module that was encapsulated in a vacuum pouch bag, allowing to remove the high-temperature sealing process needed when a thermoplastic sealant is used. Here I obtain a 60% efficiency increase with respect to a standard module. It must be noted that these values are calculated on the active area of the devices, but this gain will increase even more if the total area of the device is considered. When it comes to flexibility, I try to find some solution to simplify the handling of the liquid electrolyte of the solar cells. I did some testing using a PVDF membrane that Dr. Mara Serrapede is studying in our group. I did some preliminary tests on these membranes and observed a 43% efficiency loss with respect to a standard case with liquid electrolyte. Here, it must be noted that the efficiency loss is mainly due to the reduction of the photogenerated current, which we will try to avoid, reducing the thickness and the membrane and fine-tuning its condensability. On the other side, I started to work on the possibility of using transparent polyimide as a substrate to fabricate the photoanodes of the solar cell. This material can withstand up to 300 degrees, so it could allow a sintering temperature much higher than that allowed by other plastic substrates. So I compared the performances of photoanodes fabricated at this temperature, and I obtained a 30% loss in efficiency with respect to a standard photoanode, which for me is a good compromise if I could gain flexibility in my devices. And finally, with my colleague Marco Reina, which is working on laser-induced graphene supercapacitor, we try to exploit the high surface area of this graphene-like material to substitute the expensive and often unstable platinum counter-electrodes used for standard Dyson-style solar cell. Using these materials, we obtain only a 2% loss in efficiency with respect to standard electrodes. Then, we fabricated also a first prototype of an integrated harvesting and storage device, where 3 of the 4 total electrodes are laser-written on a flexible polyimide substrate. We were able to charge the supercapacitor to a potential very close to the maximum output voltage of the solar cell, exploiting only an artificial LED light. In the future, I will definitely keep working on open projects to obtain new prototypes. I will investigate more innovative designs and solutions, and I also want to focus even more on the real-life application and compatibility of my devices. Thank you for your attention.